And we're back. So I just left off talking about, could we have an infinite continued fraction? So let's take a look at something like that. The short answer is yes. There is some work to be done showing that we have convergence, if that's something you are interested in. But for right now, let's just figure out what one of these would look like. I'm going to pick a very simple expansion. All of my numbers an are going to be 1s, and try to figure out what it should be. Leaving aside the question of, does this actually converge to a number and make sense as a real number that I can do arithmetic with? So if I unravel my continued fraction notation, this is telling me I have an integer part 1, and then I have 1 divided by something else. That something else is a 1 right here, plus 1 on 1, plus 1 on 1, plus 1 on 1, and so on. I don't know what this number is. I can tell that it's a little bit more than 1. For right now, I will just call it x, and I'm going to try to use some algebra on it to figure out what number x has to be. So like I already said, x has to be greater than 1, because I know its integer part is 1, and then it has some fractional part added to that. So there's not a whole lot I can do on it, but in the previous chunk of this lecture, I was just saying that having the continued fraction expansion makes our algorithm really easy. I claim that x will actually just go to itself if you do the first step of the continued fraction algorithm. So in terms of the notation, I said we'll just get rid of this number, chop it off, move the semicolon over by 1, and now my integer part is 1. And the next term I get is 1, and the next term I get is 1, and so on. It didn't actually change anything. So this is a fixed point of the map here. Well, okay. That's a little strange, but what can I do with it? Back when I was using algebra to calculate this algorithm, I said, well, I'm subtracting off the integer part, and whatever is left over, I take the reciprocal. My integer part is 1. This x has an integer part of 1, and then the reciprocal of that will just be 1 divided by x minus 1. Cool. This is how I calculate the next number to look at for my algorithm. And I claim that number is x again. I take 1 on x minus 1, I get x. Well, cool, that's an equation with an unknown. I can solve that using algebra. So I will multiply through to clear that denominator, move everything over to one side, and I've got the polynomial equation 0 equals x squared minus x minus 1. Cool, it's a quadratic. I know how to solve those. I use my good old quadratic formula. So b squared plus or minus, aha, said that wrong, ha. Negative b plus or minus b squared minus 4ac divided by 2a, plug that all in and I get 1 plus or minus the square root of 5 on 2. Now I know that this x has to be greater than 1, so I'm going to have to take the plus here, and it turns out that my x is 1 plus the square root of 5 on 2, which is the golden ratio, if you're a fan of the golden ratio. So this infinite continued fraction, 1 plus 1 on 1 plus 1 on 1 plus 1 on 1 plus 1 on 1 and so on, gets me the golden ratio. So phi, but not the Euler phi function, the actual constant from geometry. Now, I do need to clarify what I mean by these infinite continued fractions. So technically what's going on is I'm only able to evaluate finite continued fractions. I would write out my formula, try to condense it all down into a single numerator divided by a single denominator, right? That'll get me some rational number. That'll always get me some rational number if it's a finite expansion. And then my infinite continued fraction is just the limit of those guys, if that limit exists. And it does exist. I only want to have one proof in today's lecture, so I'll leave that one in the notes for you to take a look at. This is exactly the same way that infinite decimal expansions work. So the mathematical constant pi is an irrational number, and when we say that pi has an expansion 3.141592635 and all the rest, really I'm saying that pi is the limit of these particular rational numbers, where I pick some n, I go out n places in my decimal expansion, that's going to be some rational number, and as you go in the limit, as n goes to infinity, all of these fractions get closer and closer together to the value of pi. So all of these rational numbers should be getting closer and closer together to whatever number this is. So anytime you see an infinite continued fraction, there's really a limit lurking under the surface. Same as anytime you see an infinite decimal expansion, there's really a limit lurking under the surface. So I claim that if I have some real number alpha, I'll use Latin for my integers, and I'll use Greek for my real numbers. If alpha is a real number and I have a0, a1 up to an, my finite continued fraction expansion, how did I get this? I just used the algorithm n times. Then I claim that alpha is in fact the limit of those finite continued fractions. So the payoff is that every real number is equal to its infinite continued fraction expansion. Every single real number has one of these expansions, just the same way as every single real number has a decimal expansion. Okay, cool. That's interesting. It's cool that I have a new way to represent any real number that I want. But I got into this because I wanted my fractions to approximate the real number. I wanted to say decimal expansions are too cumbersome. I want to find a very efficient fraction to almost be equal to alpha. Well, that's okay, because these rational numbers, right, these truncated continued fractions, or these finite continued fractions, they're supposed to be getting ever closer and closer together to the real number alpha. So these numbers will work as approximations to alpha. So we got a taste of that working with pi on the previous lecture. Today we're going to be focusing on some arbitrary number alpha and talking a little bit about how well this kind of approximation can work. So I need just a little bit more vocabulary. Again, I have some alpha as a real number. Its infinite continued fraction expansion consists of these integers a0, a1, a2. There's infinitely many of them, and we can pull out as many as we like using the continued fraction algorithm. Any fraction, a0, a1, but stopping at an, That's a special fraction because it is approximating alpha. It's supposed to be close to alpha. So I'm going to call this fraction a convergent of alpha. That's my new vocabulary for today. So make sure you're staying on top of what a convergent is. And I know that since this is some fraction, it has a numerator, I'll call Pn, and a denominator, Qn. So n here is telling me how many times I use the continued fraction algorithm. And at the end of that, I get some fraction. And I want this in lowest terms, so my p and my q are relatively prime. Another way to say that, they have GCD equal to 1. This line right here is just a restatement of my claim from the previous slide. In the limit as n goes to infinity, the nth convergent, Pn divided by Qn, should be tending towards alpha. So these numbers will be getting ever closer to alpha. And that's great in the abstract, but we need to do a little bit more work to, again, make this a practical concern. So that will be the next chunk of this lecture. See you in a bit.